can say about how to design these things, how to use these things. In the third talk by Randall Bryan, they talk about Google. What Google has done is to invent a new way of doing computation. They did not intentionally invent it. What they do is they were doing web search and everything, and then they realized that in doing this at a massive scale, right? Thousands of servers running at the same time, unreliable links, unreliable processes, they are able to come up, they're able to solve very huge problems, data-intensive problems, using this way of solving problems. And they have a name for it, it's McNamee. So this one is parallelization on a massive scale, unlike the multi-core. Multi-core is linear parallelization, right? But this one is massive parallelization. They are already doing it. Every day they have hundreds of applications running on their network using McNamee. But the science for this is not yet done. And in fact, the whole point of this guy's talk is that this is a new programming paradigm. We have to learn how to use this new programming paradigm. Now, if you are a computer scientist, the first question is, what kind of problems can be solved with this paradigm? What kind of issues are there? When you have parallel distributed computing at this scale, remember that there are scientific issues. And one scientific issue that I mentioned before is this issue of time. How do you formulate the notion of correctness when you have this massive computation, geographically distributed, unreliable component, unreliable links? The fourth talk is by Scott Shanker. And what he was trying to sell was the following, that the computer science community must come together to redesign the internet. The internet was started 40 years ago for a totally different environment. It was never meant to carry the kind of traffic that's being carried today, like your MKT traffic. It was never meant for electronic commerce. But now we're using it then in this fashion, and all the shortcomings are coming up, and they just patch it and patch it and patch it, and the big shots are saying, no, we can't do this much longer. Or else it's going to break. So they are coming up, they're thinking about, they have already started redesigning the whole internet. Now think about it, right? Here is this major enterprise where computer scientists are coming together to redesign the network. As a computer scientist, don't you feel that it is a chance for you to shape this enterprise, to shape this initiative? It is time for the computer scientist to say, no, this is how you should build the network. You should not do it this way, you should not do it this way. Now notice how this is totally different from the classical sciences, right? Classical sciences is something is already out there, you want to construct a theory for it. Here we are saying, we construct the theory first, then we build it. Or at least that's one. And it's not anything new, right? In fact, from the very beginning, computer science has been flavor. Remember Alan Turing. When Alan Turing wrote his paper about what is not computable, that was in the 1930s, way before computers as we know it existed. And yet he was able to write this paper about what is computable, and this paper is one of the cornerstones of computer science. Right? So this is a paper that precedes the technology. So computer science is different in the sense that you have to build. It is every 5 years or so you have a new hardware technology, a new software technology, and you have to construct a new science. And because you have to construct a new science, you have to be in the habit for doing this. You have to know how to build this theory. And in fact, in the case of the internet, I'm saying that you have to build the theory even before the technology. So the science has to inform the theory, the engineers. But you don't do computer science. Most of you are not interested in computer science. You don't want to do computer science. You want to do maybe programming. You want to do something more sexy. You want to maybe do animation, maybe write programs for fighter jets. Now this bug is not well known. There are other bugs, way more well known and way more expensive. Expensive in terms of dollars, expensive in terms of reputation. The Pentium bug, for example, cost Intel a lot in terms of reputation. This is a major conflict. Now, the aerospace bugs, they are embarrassing. You lose the entire satellite after sending it all the way to Mars. That is totally embarrassing. Well, where do these bugs come from? So if you look at the case of viruses, for example, one of the most successful ways of creating a bug or a virus is by exploiting buffer overflow. Okay, so buffer is just a region of memory, an array. Think of it as an array. An array is one of the most basic data structures, right? The first basic, aside from the integer and the real number, aside from a byte or whatever, the array is the most basic. And this bug just came from a failure to understand the limits of the data structure. And this failure to understand the basics of the data structure, the limits of the data structure is a failure to understand this. Draw the analogy is a failure to understand the definition. You have to. This is why in this course I insist that you learn to work with definitions. Now in school at high school or JC or whatever, the only way you learn is by looking at examples. Show me 5 examples and I know how to do it. Right? I don't know how to do anything before you show me examples. But no, there is no end to examples of software. You have to learn to work from specifications, and working from specifications is working from definition. The other reason, now the data structure is only the beginning point of a program, right? The main thing is the algorithms themselves. Now if you think about the algorithms, no matter what programming language you use, the programming language is the one that's supposed to translate the algorithm into runnable code. No matter what language you use, the very first control statement, the first kind of statement they teach you is an if-then else statement. The if-then else statement is just an implication. So if the reason why I make you do all this proof